quantum period theorem for toric Fano surfaces.
Okay, thank you for the introduction. This is our joint work with Hansol Hall and Yichen Lin. And as you will see later in my talk, a lot of our work is inspired and influenced by the work of Fukaya and his collaborators. So before, yeah, this is just yeah, nothing happened so far. And I want to thank Kenji. So before I start, I just want to thank Kenji for the wonderful work and happy birthday. Okay, so let me just recall something very classical. So let me begin with some mirror symmetry motivations for our work. Okay, so as you see in my title, I want to consider mirror symmetry in the situation that the A side is just a toric Fano sympathetic manifold. And B side is usually given by LG model. In this case, it's really the simple Horiwata mirror. And then the constraint mirror symmetry conjecture in this context just says that we have an isomorphism between quantum cohomology of X and what's on the mirror side is a Jacobian ring of W, which is a regular function about the partial derivative of W. And in this context, you can furthermore consider, so why I say this, I mean the small quantum cohomology, right? But in this case, you can further consider for each ambient cohomology class B, I want to deform this quantum cohomology. So I want to consider the B quantum cohomology deformed by ambient cohomology. And this, you still want it to be Jacobian ring of some deformed superpotential. So far this WB is just a formal deformation of the original Horiwata guy. And under such a context, there's this work of Fukaya Otaono that they really define. So a priori, this Horiwata superpotential doesn't have any meaning, but or so does this deformed version. But their work really defined this WB in my writing from Lagrangian Floor theory, which I will introduce later. So they proved star as an isomorphism of what's called Frobenius algebra. Okay, so what this is just a associative ring with a non-degenerate pair and satisfy certain relation. For example, if I take the Pontryagin pair ring here. But this is true for every B. So now, as B vary, you expect the star to be promoted to isomorphism of what's called the Frobenius manifold. On both sides, I should say, so far it's just like formal germs near this cohomology, and on this side you will consider a certain germ in the unfolding space of this superposition. Okay. And then what you expect is that Okay, so under such a situation, since what this Frobenius manifold is that it's just on tangent spaces, Frobenius algebra, and then in particular I have this family of non-degenerate parents on a tangent space, and in particular I get a metric on this Frobenius manifold. And then, respect to this metric, you can ask question like, what are flat coordinates for this Frobenius manifold structure? So this is just defined if I have metric, I have a Lewis-Civitar connection, and i.e. the flat coordinates is just some coordinate ti such that they're flat with respect to the connection. Okay, and such a question has been studied, by a lot of people already, like Giventhal, Granikov, say Sabah and Iritani. But our perspective is that we really want to take this W2 coming from the Lagrangian floor theory. So we want something to be enumerative to take on this side. Under such a situation, there's only this. So as far as I know, so if you want the WB to be further enumerative, so there's this work by Mark Gross, studied this for people, using tropical geometry for the, I will talk about this later. So our goal in this talk, as you can see, we're just, under these contents, generalize this a little bit to study this for final services. Okay, so that's our goal. Any questions so far? Okay, so let me just set up some very basic stuff about, like I said, I want to develop you what exactly what I mean by this. So the setup of our result later is that X, which is a Fourier final surface, and we denote pi to be its monomap. And okay, if D is further said to be the toric divisor, we know that away from this toric entity of canonical divisor, which I will call E0, which is the interior of this polytope, this map is a smooth SYZ fibration. Okay. And in particular, what I want to say is that as far as this fibration, I want to recover both this W and WB. But this is quite classical. What people do is that, for any view in the smooth part, I can just consider the corresponding Lagrangian torus fiber. And I will take some relative cohomology class, beta. To each such a beta, you can assign a so-called Maslov index. So this guy is Maslov index. But in this toric setting, final setting is really just 2 times the intersection of this class is a boundary divisor. Okay. Then you can just define the Horigafa mirror as such. So, W say W of U is a count of mass of two disks with one boundary mark point. So if this is LU, then I count all holomorphic disks with one boundary mark point. So mass of two just means that I intersect the boundary divisor once. And then I weigh this boundary area. So this is a weighted expression in the blueprint of H1 of this torus. So I'm taking boundary of this class, which is this loop here. Okay. Once you trivialize this, in our situation, this is quite explicit. There's some Laurent polynomial in two variables. I'll do an example later. So that's a theorem of H1. Oh, it says that if I really just count this mass of 2, I will get back to Horvath. But I don't want to consider this original superpotential. I want to consider a deformed version, right? So I still want to define another superpotential for you by taking an ambient cohomology class. So maybe I should say that in the work of Otano, they already, so if my ambient cohomology class is a divisor class, they already compute this for the bulk deformed. So this guy we'll call the bulk deformed superpotential. But if B is coming from H2, this has been computed. So, for this reason, I'll be restrict to myself. So I want to define WB for B taking. So I mean, surface case, the only other class I'll take is H4 class. Okay. So this say that it's Poincare for a point situation, and then this potential is just defined by I count such a disk, but then I furthermore intersect this disk with ambient cycle constraint given by points in this case. Okay, so to do this, let us consider this. So let me just define this for you. So consider this space of homomorphic disk with one boundary mark point and L interior mark point. Okay. So this is a big modular space of border disk with one boundary mark point. And L interior mark point. So I want it to be homomorphic with respect to the standard complex structure and represent this class. Okay. And then I also have to ask this points in the interior passing less than X. So we'll compactify this space. Okay. So so from this space, you can define like evaluation map. So I'm just trying to formalize how this intersection with ambient cohomology classes defined explicitly. So since I have interior mark points on this big modular space, U to X. I can just, L interior mark point, I just can evaluate them inside X. And then I want to represent this class in H4 here. But here the subtlety is that I don't, so in the original case that Guy and collaborator consider this class has to be T2 invariant. But we don't necessarily consider that. So then, if you don't necessarily take T2 invariant, the representative of this class of H4, then you can just take any points. It doesn't have to be Turing invariant, right? So I take L generic mark point. say Q1 of QL. I will denote this like such. And I form this fiber product. So I just ask the interior evaluation map to be mapped to this cycle constraint that I form. So this is a familiar modular space. The virtual dimension of this modular space is, so if you notice, it's n-3 plus the Maxwell index of beta. And then I added the 2L mark point in the interior, but it passes through codimension 4 cycles, so minus 4L, and then plus 1 boundary marking. Okay, and we're in dimension 2. So due to this virtual dimension, you can check that the so if your class now is of mass of 2L plus 2. So such homomorphic and then you require them passing through L generic mark point. And this virtual dimension will behave like the original mass of 2, right? So such a disk will behave as the original mass of 2 disk. So due to this reason, I'll just redefine this to be some called the generalized mass of 2 disk. And then I will use the notation mu tilde of beta, sometimes to short it. Then under this setting, you can really just for the bulk deform the zero potential you are interested, you can write down an explicit formula for it. So really order by order. So define WK U to be the count of all possible generalized mass of 2 disks. Okay, so I still have one. I use up all the internal mark point. I still have one more boundary mark point. So I use this. So if you calculate this dimension is dimension 2, then I push forward this to the cohomology of cohomology of L, and then take the degree of this to be the generic count in this situation. And it's still weighted by the boundary contribution. But in order to, write this as a formal deformation of the original one, or keep track of the bulk insertion, it will also weight this by T to the L, for if I'm passing through L mark points. So now this is still, so this expression in some Laurent series. Formally adjoint T, so if I'm WK, then this is a case order deformation. So this is a case order deformation of the original one.
So you said this behaves like MATLAB 2 in the sense that if you count, there should be this passing through a point.
Yeah, generic count. So this is still a generic count.
But is this expression really independent of where these points Q1?
Oh, no. So there will be workhouses. Also, like this expression will depend on U as really. So this is really depend on U and then the point.
What was U again?
U is the Lagrangian boundary condition.
Okay.
Yeah. Yeah, it just might be.
That's clear, but it's more the wall crossing.
Yeah. So yeah, thank you for the question. So this is exactly where this superpotential will be different from the Fourier-Massey ones. So Hoare alpha will, in this simple case, have no, so well-defined wall crossing, right? But in this case, if you consider the bulk deformed superpotential, there will be a lot of wall crossing happening. Yeah. Depending on
Since
where.
bulk cross is not equivariant. If you take equivariant cycles, there's no wall crossing either.
Right,
Yeah.
exactly. So there's also, this is also only happening because I'm taking a non-equivariant. So I'm not, for example, I'm not taking the invariant toric points on the boundary. I'm really taking, so by saying this, I'm really taking points in the interior, say.
I just have one more thing to
Sure.
clarify. So, if to define the K, I'm calling it order K part of it, there's some invariant that is associated with having K points,
Yep.
and one that's having K minus 1.
Right, so this is low, all the disk that's less are equal to
Yeah, but you assume that the set of points that you use for K minus 1 is a subset of, are they, I'm a little confused, like, is there some kind of ordering on these points that we're using to define this?
No, I mean, right, I mean, if you want to do this for all number of points, you have to, of course, this is computed inductively, right? So order by order, you say this, for the next order, I have to, this is a subset of the next one.
Okay, that's what
Okay. But in fact, the ordering doesn't matter, but I need this to be an order subset. So that's exactly, okay. So this wall crossing phenomenon is exactly what I want to say next. So this bulk deformed motion will actually experience wall crossing. For example, it means that it depends on the choice of U and this finite set of points. And let me just do a very simple example here. Okay, so again, for simple example, we just restrict to P2 again. You know, this is moment polytope. And just to set up notation. So for P2, I pick a Lagrangian fiber over the point of interior of the moment polytope. And then there are 3 disk classes. One intersect this boundary divisor, one intersect this boundary divisor, so that their boundary contribution is homology class in this, each one of these torus is given by the following. Right. Then you weight this, you will see that, so now in our notation, W0 of U is going to be the familiar Hoare-Alpha potential of P2, and in particular, well-defined independent of U. If we ignore the Novikov coefficient.
Can I ask something?
Mhm.
So how do I know that this is a number for generic
Oh.
chosen one points?
Yeah, so this is actually something we proved. So for this superpotential in this dimension, you, so first of all, this Lagrangian boundary, Lagrangian torus at that peak cannot be on the walls of this, you know, so it cannot bounce mass of 0. I mean, it will bounce in the end, but if it does not, I mean, for generic torus fiber, it does not. So you can define this for generic torus fiber. So there's no, you know, there's no sphere bubble and also no generically, there's no mass of, I will talk about this. So there will be like generalized mass of 0 disk that this can bound. But for generic torus fiber that at peak, there's no such a disk by dimensional reason.
This is a specifically toric thing? Or
It's just some dimension calculation with the with this modular space.
so if I took like a Del Pezzo surface and a Lagrangian torus,
Mhm.
the same thing. True.
I think so. Yeah. I mean, but it has to do with some this dimension. I mean, 2-dimension and bulk deformed by H4. But I mean, really, the argument is dimension count. So yeah, that will work. But I'm not sure about other degree and dimension. So yeah, as Paul said, I mean, originally we count this maybe some partial count, but in our case, if this does not bound mass of zero, then this can be really defined as a generic count.
I mean, generally speaking, the modular space of disks could be not smooth,
Um,
right?
right, but
Saying the virtual dimension might be.
No, I mean, M1L
mhm.
could be horrible, right?
So in this
Yeah.
case, like, if the homomorphic, the Lagrangian boundary doesn't bound generalized muscle in zero disk, then all the relevant modular space are actually smooth.
Yeah, I mean, I'm claiming.
True, toric and
So that uses the toric condition.
yeah.
Okay.
So toric and
special
Fano.
We
to
don't
toric.
need it, if just dimension 4, and Lagrange summing 4, and muscle limit is 0 and lower, Gaussian dimension is negative.
I need
There's no
a.
mark point. Then you can perturb it away. And only muscle index 2 is non-trivial.
Yeah, but the concern is with additional interior marked points. So there could be some high-dimensional moduli space of disks.
Yeah, but then if you just put the necessary condition, you can just reduce the dimension by 2, or 4, by even number. So the generalized muscle means just after insertion, the virtual dimension just comes.
Yes, but those moduli spaces don't need to be smooth. The ones that you get with.
It's not smooth, but it has a fundamental class.
It has fundamental, then you need to do.
I think in this particular case, the modular space are really smooth.
Yes,
They're
that's
really
it.
coming.
Yeah, I mean, really claiming this is.
I really need toric and Fano.
Yeah. Okay. Okay, so here I want to give you an example of what I mean by this. So this is usual horizontal potential, but if I do P2 with 1 point, say, okay? So still the monopolytotal is like this. And the projection of this point says here. Then, as I said, in this case, you can calculate this dimension. So now, like mass of 2L disk can be generalized the mass of 0, right? And well, let's say we're just 1 point. So mass of 2 passing through 1 point is mass of 0. So then you can, and there's generally such a no Lagrangian bound such disk, but if you are lying on the locus of these lines, because if you are here, you know this Lagrangian bounded disk in this direction passing through here, right?
Doesn't it depend where your point is?
Yeah, it depends on, this is a projection of, this wall depends on this point.
So, that's the point. Where's the
That's-
torus? The torus can be anywhere.
Torus is on this line.
Okay, okay.
If my torus fiber is anywhere along this line,
Yeah.
then I know there's a disk here. Okay. So just by the previous calculation. So then you can express it. So these are the torus that bounce mass of 0, and then so in this example, in this chamber, the W1 will be given by n plus yeah, let me first write this out. Okay, and then why is that? Because, okay, if I'm Lagrangian torus fiber over here, I still have the original 3 disk, but it's also possible I have a mass of 2 disk passing through intersect this boundary divisor and this boundary divisor. So there's one more contribution. This term is coming from this intersect this two boundary divisor and with Lagrange boundary condition here. And then you can play around with this.
Sorry, can you run that this again? Can you just point it out again?
Oh, okay. So I have a mass of 4 disk. So this is the point I want to bulk deform by. So I have mass of 4 disks passing through this point. I mean, this is a heuristic drawing, but we'll see that they use this later. And then it's this count because you don't grade by this direction. In this direction, it doesn't pass in through the toric divisor. So it's 1 over the Z2. Okay, so we do see there are some walls that can appear already if I add 1 point. So in general, so I still want to study this, or we want to study this order by order. So let's denote the holomorphic wall in this case. So you can see there's a lot of mass of index of different. If I add L generic mark point, there are many higher mass of contribution can contribute to this. Okay, so I just define this holomorphic wall to be the locus of Lagrangian fibers. These fibers that bounds, say, generalized mass of zero disk. And by this again can be mass of 2L passing through L mark points. Okay. So the theorem I want to talk about is that so the theorem from last year is that still under the setting, X is for follow surface. And then if we are taking L to be a Lagrangian fiber that does now lie over the wall, so U is now this holomorphic wall, then what's true is that we can compute it. This WK order by order can be computed inductively for all K in each chamber. And part 2 is that relate back to the title of our talk is that there's a I would call a big quantum purity theorem sort of statement, which says that so if I just take this superpotential or WK that I define, then I consider this sort of also accumulating integrals over T2, and I raise this to WK or H bar, this formal parameter. And let's take this omega to be the torus standard form. So there's some integral, pure integral you can consider on the B side. And in particular, you see in my WK, there's a formal parameter T, and then also here I added some formal parameter H bar. So the theorem says that, okay, now I want to expand this exponential, I want to expand it, and order by order, you can write it as a polynomial in T and H bar, and then what are the coefficients? The coefficient is exactly given by the descendant model between, right? Okay, so this is a big expression, but I'm interested, say, order by order, in H bar and T to the n. I want to tell you the coefficient here. So, so H bar is a formal parameter to keep track of the descendant power that I want to put here. Okay. So you see, I took some points over there, algebraic outcome. Maybe for any number that's less than k, I can deform my correlation function as per psi minus 2u. Okay. And then by this I really mean the log omega. And then in class delta. And for this to be a generic count, you have to take curve class delta, so that these are just formalism. You have to take to be the n plus n degree, so that this is a generic count. And where again, this denotes log weighted invariance of the Torre final surface. Sorry, this is descendant ones that I inserted per side class in the last marking. So it's big quantum period because you further deform the original 1.8 Gromov-Witten invariant by some ambient class. So maybe I should say, in this formula we really inserted the Hong class, but we could have done this with H2 too.
What are the subscripts? Sorry, cubes just 1 through that?
I1,
I1.
yeah. Yeah. Yeah, in fact, okay. So any other n subset of this original set. Sorry, I'm missing. So this actually have to derive by automorphism of this class. For some reason, I will explain. So yeah, okay. So that's the statement of our theorem. So let me give some remarks about this theorem. So as I said, this part of the theorem was part A. So recovers Gauss's result for P2. We can also do this for P2. And in fact, the way we prove it is via atomical geometry, so I will elaborate on this. But there's an interesting aspect is that you see, when I consider this oscillation integral, I'm only integrate this on the compactors T2. Okay. So in particular, so this the sort of integral that I consider. This one gives the first flat coordinate, which is the monodromy invariant flat coordinate on the mirror side. Just because, a priori you see this WK, like I said, depend on U and then Walk-Cosine. But still, because the integral is perturbed by Walk-Cosine transformation, so this is still monodromy invariant. But you could have, this is discussing showstopper, could have changed this. So T2 say this mirror of a skyscraper shape. And then I could have used the structure shape and integrated on positive real locus integrate this over the positive real locus on the mirror side. When I take the log map to the base.
Which is not compact.
Which is not compact. But as we're being told by show that the result will give you some gamma class on the A side. It will involve some gamma class. But you see, like this type of result, I really want so I know the Gomorrhian, like say one point descendant is flat coordinate on the A side, and they are really supposed to be rational numbers. There's no zeta values. So at this point, the challenge is that, at least to me, is that if I want to find other coordinates, I'm supposed to write down a linear combination of this cycle with the positive real and other real class that I take. So that altogether, they cancel the transcendental numbers, so it remains rational on this side. And then once you've done that, this combination will give you the correct flat coordinates on the B side. Which, by the way, Rose did this for P2. It's some complicated calculation if you're interested. But so anyone knows how to do this, I would like to know. Okay, so also, I mean, let me just mention there's a recent work by Tomalog proved such a theorem for W0, but really for all final or monotone symplectic manifold. So it's quite general. If you're interested, you can look into it. For the remaining, so that's the statement that status of this theorem. So again, like a lot of people have studied this, but the question here is that how do you find the correct cycle to integrate so that when I expand order by order, I just get the Gomorrhian invariance. Okay, so let me tell you. So I'll focus on the proof of part B, but if anyone interested in part A, I can also tell you. In particular, this use this of Kaya's pseudo SOPOB for family floor and workhorse implement tools. Okay. So for B, I'll tell you our approach. Maybe tropical geometry. So as I said, our work is just motivated by this work by Gross. So let's go to the realm of tropical geometry. Again, let me just recall very briefly. So if you're given a slightly vibration, smooth isoelectric vibration will be now. There's two integral alpha structure. This means the transitions are in GLZ semi-direct product line translation. These are the symplectic and complex integral alpha structure. But in the case of Torrefano, if I consider complement of this toric divisor, these are the moment map that I considered before. So this is the symplectic alpha coordinates. And you can also consider this log map. Just take two. So this is in particular, in our case, say star square. And then just take the normal of x and normal of y. So this maps you to R2. Okay. So this is really the same manifold in these two coordinates defined by this Legendre transform. So I want to look at this holomorphic disk. Since I want to use tropical geometry, I want to look at the holomorphic disk projection over here. So So remember we're counting some disk over here. And it is known sort of the homomorphic curves in x minus d. So this is maybe known. So they project to a thickening of a tropical curve. So as an example, again, you take this x plus y plus 1 in C star squared and project to R2. And you'll see the projection is some so-called amoeba around this straight line. So in particular, this union of straight line will be the tropical curve we talk about. So this is some curve from like a traveling graph to R2 in our case. Traveling tree, so that each edge is mapped to is a straight line in R2 and satisfy some balancing condition. Edge. Okay. But this is for tropical curve. Remember, we want to do disk counting. Okay, so there's the analogous notion for tropical disk. Capture this Lagrangian boundary condition. But now it's some rooted, maybe traveling graph tree. Like an example of such is that it can stop by some Lagrangian boundary condition. Say projection of U in the base, right? And in particular, you can also you can consider with mark points also, since you want to do bulk deformed case. So this is a following idea due to Gauss and Sieber. So now what I want to do is that, what I should say is that here I want to prove this theorem, but I want to prove it via tropical geometry. I want to replace this holomorphic gadget with a tropical gadget. So I want to, so using this, there also exists a definition of WK tropically. So where I denoted as W chop, okay. You can just count such a thing. Okay. So the idea now is just that I want to count holomorphic curves, but possibly also disks with bulk inversions. But I know that if I project by log, they become either tropical curve or this marked or tropical disk with mark point. And then the paradox, if you're really a tropical curve, is work by Nishino and Sieber. Now you can, so given such a curve, you can really find the corresponding log for Moetten count. In X relative the toric divisor. So I'm using this big theorem, and also, so this is only, their theorem works for tropical curves, but in the end I will need to appeal to descendant, so this is another recent work by Mandel and Rudak. So they really just use the original argument by Nishino and Zebert and then generalize it to with the descendant insertions. So in their precise class. So so this is, well, this part is just being used. So essentially our theorem is that we prove this tropical holomorphic correspondence here. Prove this. And also the non-trivial part is for holomorphic disk counting, or disk counting. Okay. So let me just tell you a little bit more about this argument. So essentially you want to So I have a holomorphic sort of potential, of deformed potential, also a tropical one, and I could have I can compute them in each chamber, and so for each chamber I know there's some argument to show that the Wall-Cauchy map they really agrees, and so in order to really prove this holomorphic potential with this tropical analog, for us it really suffices to match the walls, match this holomorphic wall that I defined with the corresponding analog of tropical walls. Okay. And for example, again in P2, so what are holomorphic walls? You see, for example, this obvious example, you have, well, so now I'm drawing the corresponding tropical curve, where you should imagine there's some holomorphic curve on the top, passing through 2 points. And then, so now you're being asked the question that even if you give such a holomorphic disk, and then how do you, so given such a holomorphic disk, I want to close it up, right, to get a holomorphic curve. So, really given this, that maps to X with boundary on L, there is, since this is really a holomorphic map, there is a unique extension of this that factors through a map to P1. Now you want to, just by unique, so now you want to find this curve explicitly. So our method is really use the anti-symplectic involution of say star square. In particular, it's defined by just x, y ascending to x bar y, 1 over x bar, and the 1 over y bar. Okay. And under this anti-symplectic involution, I can just, so there is such a, I would say doubling that. So you want to know where the other half of the holomorphic curve goes, right? And we'll say the obvious one under this involution is that you just take the Z2 symmetric image. So say I move you this boundary condition to 0, 0. Under this involution, you'll get this curve. Okay, this is some closed curve and extend to P1. And in particular, some in this example is some degree 2 curve in P. in P2. At least, this is something maybe I expected from tropical geometry perspective, since naively you might think, given such a curve is a stop, so what people sometimes do is that I could have just extend this Lagrangian boundary condition to infinity, and then extend this holomorphic curve as a honest degree 1 curve in P2. But the difference is that if this extension wouldn't capture this Lagrangian boundary condition, you could. So if you're looking for this curve, it's really just the extension is really this degree 2 extension. And then you can use this method double any tropical curve you want. And once you close it up, you can just show that the holomorphic curve agree with the tropical curve, or holomorphic curve project to a neighborhood of this tropical curve, and you have some control of this wall. And so upshot of this is that, although I didn't define it to you explicitly, but I want to replace this by some tropical analog and by this such a discounting. Okay, and okay now given such a consequence, you can really just prove this part B, few lines. So pool of this part B is, I would say, simple, given this. Okay, so let me just begin with. So what I want to show for you, begin with some oscillating integral here. But since I have this, I already changed this to a tropical potential, as you imagine. Okay. But this is just a integral that you can do, in particular by this residual. So maybe I should say this similar argument is also used by Gross and Tonkinok. So this integral, when you evaluate it, you see that so you expand this into Taylor series, right? And then when you integrate out, you will see that only constant term of this expansion will contribute. So now I replace this to a tropical analog, and then order by order. This is my H bar. And order by order, I'm taking power of this in M. So this is weighted, auxiliary weighted in H bar. And then this suffices to understand this part. Okay? But what this really is what is a constant of some power of the superpotential, right? So for each, fix a M for each M. This right, sorry, this constant term. So you want to understand this. Okay, but pictorially, this is in 1-to-1 projection to M, in our case now, tropical disk with mark point, whose boundary homology class. Remember, this is superpotential weighted by boundary homology class. Boundary homology class is sum up to 0. So I have some curve that come into LU, possibly marked. and I have L of them. Okay, H1, H2, H3. And a priori, they're just disks, but I know that their boundary harmonica sum up to 0. In this case, then you can try to glue them. So you can study this modular space, you glue them, and you'll get a tropical curve. So each of these are generalized mass of 2 disks. When you glue them in a fixed Lagrangian boundary. Okay. So this is the corresponding gluing. Where, remember I have, when I define a tropical curve, I require this tree to be trivalent. But once you glue it, this one of the vortex becomes a higher, has a higher valency, right? So, and this is, if you do a tropical geometry, then this is exactly how descendant is defined. So this will just contribute to, in our case, maybe say some, you know, for the marked ones. So this will just contribute to this. And then the descendant power coming from. So if this and this come together, they're supposed to get a rigid modular space. You're supposed to insert psi m plus minus 2 to this mark point U. Okay, which is a tropical point. So higher weights. There are some weights in tropical geometry you have to check. Or there's some combinatorial factors, like when you take this, there's supposed to be m choose I1 to IK taken into account, but not all taken into account. These two will agree. So then you arise into this correlation function. And in the end, you can, well, compare to this result and get a mean 0, so which is not the proof.
So in this last step, do you prove the equality of this combinatorial psi class with the classical ones, or is this somebody else's work?
Classical, I mean, you mean log one?
One like classical Grothendieck theory. You said that you can interpret this psi class as, you have k-valent vertex.
Is that Mendel-Ruda?
Yeah, Mendel-Ruda, they do this. Well, this definition actually, tropical descendant is actually defined by Gross. So going back to P2.
Okay.
And he actually proved this with log moment environment. And then these people use the work of Initial Zibert to prove it. So actually this part of the diagram works for all varieties, and part of our arguments also work. So if you wanted to do this for example, for higher dimension, so our sort of the homomorphic tropical correspondence part also works in any dimension, but to really define this WK for various degree insertions will be difficult, or like if you really want to calculate this type of bulk deformed potential. But for example, in tropical geometry, they really also consider non-equivariant insertion. So this just match on the notes in this case. If you're interested, there are some higher dimensional analog you can study, but yeah.
Any other questions? Let's thank you again.